UMP-D-uppercase S my test. And here you can see there are multiple sections. Each section is a contiguous region that contains memory locations that belong together. There's one particular section called _init. It includes all the instructions that execute before a main function in C and C++ get controlled. You will also see that the output is considerably longer than that of the object file, and that's because we are linking with all the libraries, so everything that you need is in the executable. Now, the most important part is the first instruction of the main function. It is no longer 0. Because the 0 that you saw earlier, if you follow these steps, the 0 that you saw earlier associated with main in the object file is only relative to the beginning of that particular object file. This one here has a very specific memory location. In this case, it is 804840C. It is in hexadecimal. This specifies where that particular subroutine main is supposed to be loaded when you're about to run the program. So all the addresses are resolved, including where you're supposed to load the program into memory before you run the program, or before the operating system let the program execute. So are we doing okay so far with these concepts? No questions? Okay. Now when you run the program using the CLI, the output of this program is not very interesting. But when you run the program, there are several steps involved. The program is first parsed by the kernel, and then is loaded into memory. Different sections of the executable are loaded into their respective locations in memory. There are at least 2 sections that you should be aware of. One section is called text, T-E-X-T, and that's where your instructions are. And then the other section is called data, and that's where your variables, your global variables are located. Okay, so if data is only for global and static variables, where is your local variable? It is neither in text nor data. It is actually on the stack. It is allocated and deallocated dynamically. Okay, so local variables are quite special from this context because the loader doesn't know where to load the local variables. Okay, until a subroutine is invoked or called, the local variables associated with that subroutine do not exist. Okay, is that concept okay or not okay? Is that okay? All right. So if you have a subroutine that is recursive, each invocation or each instance of calling that subroutine will create its own local variables on the stack. Okay. Did they talk about this concept in C and C++ in cisp310? No, not really. Okay, go ahead.
Do computers have multiple stacks?
No.
If you run multiple programs, how does it?
Okay, that is a good question. Okay, because I'm glad you clarified your question right away. The answer is each process has one stack. No, I take it back. No, I'm sorry. Each thread has a stack. Okay, when you run a program, each program in execution is called a process. So within a process, you can also have multiple threads for multi-threading. So each thread in a multi-threading program has its own stack. But you can have multiple processes corresponding to the same program. In other words, you can run the same program multiple times, then you have multiple processes corresponding to the same program. So that's the program is static. It simply is a pile of instructions. A process is a program in execution, and you can have multiple processes corresponding to the same program. Within the same process, you can split up into multiple threads, so you can have multiple things that are quote unquote happening in parallel, if that is what your program is supposed to do. So each thread has its own stack in that case. Yeah, I'm kind of sad that we can no longer offer cisp453 because that will be the class that we'll talk about multi-process, multi-threading, how to do socket programming, and all the cool stuff that
What was 453?
It's called systems programming in C. We are no longer offering that class because the enrollment has always been very low with that class. Now, obviously, these days, that situation probably would have changed, but the department has voted to cancel that class. And the other thing has to do with only people who are transferring to CSU require that class. People who are transferring to UC do not require that class. And that's why the enrollment is typically quite low. It's because it doesn't fit all the articulation agreements that we have.
So what do you do if you require that class?
You take it over at Sac State. And that's the really funny part, because the last time we offered that class, we had students from Sac State coming back here to take that class because Sac State could not offer that class over there.
Lovely. Lovely.
Yeah, that's kind of ironic, yes. Okay, so once the operating system loads the program into memory and initialize everything, then it will transfer control to the program, starting at a label that we call _start. So _start is a very important label because it tells not only the linker, that this is the starting point of the entire program, it tells the operating system this is the first instruction, to start the entire program. Right? So are there any questions about this slide here? This slide is really just trying to relate what you already know about C programs to something that we will talk about in this class, which is a little bit lower in terms of level. Okay, so if there are no questions, we'll go back to main screen here, and we don't have to deal with instructions to use the virtual machine because we kind of spent quite a bit of time on that already. So now we are moving on to topic 2, which is really the first part of the programming side of this class. And I'll turn on, return to my normal role first. Turn editing on, because I want to change the highlight, so you know which section we are currently working with. So I'm going to highlight topic 2, which doesn't really look like there's a whole lot of material, but there is, because this is actually one pretty big slide, or pretty big chunk right here. All right, so this has to do with the 386 or I-386 instruction addressing modes. Okay? In other words, if you're adding two things, okay, how do we specify each one of those two things? That's the question that we are trying to answer here. It is called the addressing mode. We'll start with a move instruction. MOV stands for move. Most of the time, the instructions are abbreviated to only the first 3 letters, with the exception of call, which is C-A-L-L, not C-A-L. I do not understand why some are abbreviated and some are not, because move is just M-O-V-E. Why do they remove that E when call is C-A-L-L, and they kept the double L? I don't know.
That's with people.
Hmm?
That's with people.
Maybe they just didn't know that move is supposed to have an E at the end. I don't know. I mean, it's probably historical more than anything else. All right, so this is a move instruction. A move instruction in general has the following format. This is the angle bracket, the vertical bar, the angle brackets and stuff like that. It's actually fairly standard for specifying syntax. How many people you feel kind of familiar with this type of notation already? Okay, some of you, and some of you may not have been exposed to a lot of these notations. So I kind of explained what this notation means. Regular text like MOV are basically required verbatim, which means you have to specify, you have to spell out MOV the way it is specified here. If you see something in square brackets, like in this case, B, W, L, they're in square brackets, that means it is optional. Okay, it is something that is optional. You can have it or not have it. Within something that is optional, if you see vertical bars, separating the items, it means these are alternatives. You have to pick one of these alternatives. So in this case, move can be by itself without any suffix. If you decide to use a suffix, it can be B, W, or L. Is that okay? When we have placeholders, like source and destination, these are called placeholders because each one is enclosed by square brackets. Now these square brackets has nothing to do with XML. This notation was used, widely used way before XML became, was even invented. So what this means, with the square bracket, means SRC is just a placeholder for something, okay? Something to be specified later. And same thing with destination, DEST in square brackets, not in angle brackets, okay? So together, what this means is a move instruction has to start with the letters MOV. You can specify the width of the operation using B, W, or L, but that part is optional. It has two operands, a source operand, which we'll talk about later, and a destination operand, which we'll also talk about later. Are there any questions about the notation itself, the use of the square bracket, vertical bar, and the angle brackets? Go ahead.
Does the order of options matter, BWL?
Because you'll only be using one of the three, so it doesn't really matter.
You can't use a mixture of them. Like
You cannot
BW.
use a mixture. In this case, it's an alternative, which means you pick one of the options. All right. Any other questions? No other questions? Now you might find this notation used in other contexts. Like when you read the specification of SQL, they might use this notation to specify how you use, let's say, the select statement or something like that. Eventually, everything has to do with BNF, which is a standardized notation for specifying syntax, and this is one notation that is commonly used. All right, so that's pretty much what I have talked about down here. The last paragraph has to do with move. MOV is actually a misnomer, which means it doesn't really say what the instruction does. Okay, because in the physical world, we can move things, okay? You can see that I can move this eraser from here to over here. Because when I move something in real world, the eraser is no longer, where it was before, okay? There's only one eraser. I cannot, replicate an eraser, but we don't have the technology to do that yet. Okay? But when you're copying, when you are moving in the context of memory, you're not actually moving, you're really just copying. Okay? Think of a C assignment statement. Okay? That's basically what the move is. It's like an assignment statement. It uses the right-hand side to update the left-hand side in the case of an assignment statement. In the case of the move instruction, it uses the first operand to update the second operand. So the order is kind of reversed. Okay, when it comes to the left-hand side versus the right-hand side, it's reversed, but it really has the same effect as an assignment statement. Yep.
Is the syntax the same in other assemblers too, like Microsoft Assembler or
No.
Net Assembler? This field, is it right?
No, MASM, which is Microsoft
Yeah.
Assembler, uses the Intel notation. The Intel notation specifies the destination first.
This one is AT&T.
This is called the AT&T notation, where we specify the source operand first. So in this class, we are definitely using just the AT&T notation. So if you're used to the Intel notation, you kind of have to undo what you learned already in order to be comfortable with the notation here. But it's really just the reversal of the operand.